Alright guys, welcome to lesson 5.2. In today's lesson, I'm going to show you how to approximate area below a curve, a function curve, and the x-axis, or bounded by the x-axis. So before we begin, approximating the area below a curve is also referred to as the Riemann sums. George Riemann is a mathematician that has been working on areas below a curve, approximating them using rectangles, and that's why this method is also known after his last name. So you might wonder, why are we approximating areas? Well, it turns out that area and antiderivative are related, and we're going to talk about their relationship in the next few lessons. But just for now, we're going to focus on how to approximate area that's bounded by a curve and the x-axis. By the way, between an interval, this value A is called the left side of the interval. The value B is called the right side of the interval, or the right endpoint. Now, we all know that distance is rate times time, but the rate has to be a constant rate. And so it turns out that from first semester, we figured out that first derivative is the rate at which a car is moving. First derivative is the velocity. And now as we almost began second semester, we're gonna discuss a lot about integration. And integration is somehow connected to this simple formula, and I'll show you how it connects to that, in a little bit in this lesson and the next lesson. And the area under the curve, which is what we're doing in this lesson, which is finding the area under the curve. So guess what? Finding the area under the curve, antiderivative, are connected to distance equals to rate times time. Velocity connects to that as well, and we did that in the first semester. First derivative is velocity. So this is just a picture of traffic jam, and let's take a look at a simple motivating question. Let's say that a person is on the highway. The car they are driving is moving at a rate of 65 miles per hour. At 1 p.m., the driver presses the cruise control on the car and then lets the car move down the highway at this steady rate for the next 4 hours. So let's draw a graph for this situation. Let's assume that this is the mark at 1 p.m. and the person is gonna let the car cruise for the next 4 hours at 65 miles an hour. That means that the time at 4 hours later would be 5 p.m. Okay, so this would represent our time axis, and this vertical axis is going to be our miles per hour axis. Perhaps this dot represents 75 miles, this dot represents 65 miles, and so the person is cruising at 65 miles an hour starting at 1 o'clock all the way to 5 o'clock. So perhaps before the person pressed the cruise control button, the person was increasing his speed until 1 p.m. and that is when he pressed the cruise control button, which allows the car to cruise at 65 miles per hour until 4 hours later. And at 4 hours later, maybe the person slowed down somewhere. We draw the graph for this problem from the 4 hours, so within that 4 hour frame. So that's kind of like what we're looking at here. Next thing I want us to do is I want us to find the area of the region under this curve. So find the area of this region. Now, hopefully, it is a simple process to find the area under this region because this region is really a rectangle. And the way how we find the area of a rectangle is we take the width is 4, okay, and we multiply that by the height, and the height is 65. And by the way, keep in mind that this is the graph of his velocity, okay? So we take area is height times the width, and so area is 65 times 4, and that brings us to 65 times 4. I think that might be 260, but we'll see. What is it? So 65 times 4, that is 260. So the area is 260. The area of the rectangle is 260. Okay. Now, find the slope of the curve. The slope of this curve is 0, right? The slope of the curve is 0. The area of the region of the curve is 260. The slope of the curve is 0. So what do these numbers mean? Well, first of all, if you look at it in further details, when we say that area is equal to height times width, isn't this the same as the rate? How fast the driver is going? And then isn't this the same as the amount of time he drove at this miles? So isn't this the same as distance equals to rate times time, which is 65 times 4, and that's also 260. So what we can conclude is that the distance is 260. The distance that the person drove for 4 hours is 260. The area is 260. And you look carefully at how we find area and how we find distance, it's pretty much the same. It is pretty much the same. So what we can conclude is that the area of a velocity curve that's bounded by the x-axis represents the distance traveled. It represents the distance traveled because isn't that the time, and isn't that the rate? And so you multiply them together, you get the distance traveled. But if you multiply them together, if you visualize it as the shape a rectangle, then that's also the area of the rectangle. So area is the distance traveled. Okay. All right. So that's what that number means. Area is the distance traveled. And what does the slope mean? Well, the slope of 0 means that the car is not accelerating. The car has an acceleration of 0. That means the car is neither speeding up or slowing down, which means that the car was moving at a constant speed. And so how far did they travel in 4 hours? They traveled 260 miles in 4 hours. So one of the main applications of area is to help determine the total change, and this total change could be the distance, or it could be the total amount of perhaps oil that was spilled in the last 4 hours, and so on and so forth. Okay. All right. Now, in general, we're not going to be able to drive at a constant speed on the freeway. There will be times where we have to slow down, we have to speed up, and so on and so forth. So it is very rare that we're going to be moving at a constant speed for the next 4 hours. Therefore, we have to develop a method to determine the distance traveled in the next 4 hours or in the last 4 hours, assuming that our speed will change over time. When our speed changes over time, it is possible for us to graph the graph of our velocity, how fast we're going, when do we slow down, and so on and so forth. And if you're able to graph that, and if you're able to find the area below the curve, perhaps when we started at 1 p.m., we went at the speed, and then our speed changes for the next 4 hours, So then at 5 p.m. we ended up going at this speed. So the question here is, how far did you travel in the last 4 hours? To answer that question, we use calculus. And in calculus, if we're able to find the area of this region right here, then that area represents the distance traveled. So calculus allows us to find the distance traveled, and that's what a car's computer will do, or perhaps your phone, when it says that you have traveled 20 miles over the last 30 minutes. It means that inside it's programmed to sketch the graph of the velocity, and then it was programmed using calculus to find the area under that curve over that time frame. That's how it's able to tell you that you have traveled 20 or 30 miles. Now, finding the exact area under this curve can be achieved, but it is extremely time consuming. So one of the best thing we can do is approximate the area under this curve. And by the way, when I say that it's time consuming to find the exact area, I'm referring to just the methods presented in this lesson. In the next few lessons, I'm going to show you a method on how to find the exact area quickly and easily. But for now, we're just going to stick with approximating the area using traditional rectangles. So there are three methods that we're going to discuss. They are the RRAM, LRAM, and MRAM. Now, RRAM stands for Right Endpoint Rectangular Approximation Method, also known as the right-Riemann sum. LRAM is Left Endpoint Rectangular Approximation Method, also known as the left-Riemann sum. MRAM is the midpoint. I should have said midpoint. Rectangular approximation method, also known as the midpoint Riemann sum. Other terminology that you need to know before we begin: A will stand for the left endpoint of the interval. So A will denote the left endpoint. So A would be like 1. Okay. B stands for the right endpoint on your interval. And then you have to decide how many rectangles you're gonna create to approximate your area. And so N will stand for the number of rectangles. And then once you have determined the number of rectangles, then the width of each rectangle, which is perhaps, I can try to approximate the area under that curve using 4 rectangles, and then each one of these will represent the width of my rectangle. So the width of the rectangle can be calculated by taking the difference of your given interval and then divide that by the number of rectangles. That gives you the width of your rectangle, and the width is one of the numbers needed to find the area. So that's why that needs to be calculated. So in a typical problem, you will be given A, B, and N, and you have to calculate the width. And then of course you have to apply the formula on how to find the area of a rectangle to calculate the areas of all the rectangles. So let's start with the first method. We call that the LRAM, or the left Riemann sum. We're gonna approximate the area of the graph of x squared plus 1 from 1 to 3. Now the exact area of the graph between 1 and 3 is this region right here. And we're gonna try to use rectangles to approximate the area of that region. So to begin, we need to know the method we're using, which is LRAM, left Riemann sum. We need a function, and we're given an interval, and we're gonna use 4 rectangles of equal width. All right, so look, we know what A is, we know what B is, we know what N is, and our only job is to find out the width of the rectangle, so we know how long to make each of the width. So we begin the process by identifying what A, B, and N's are. So A, our left endpoint is 1, our right endpoint is 3, and then we want 4 rectangles, and then we use that information to determine our width. And so it turns out that our width is going to be 1/2, because 3 minus 1 is 2, and 2 divided by 4 is 1/2. So our width is 1/2. So we want to start at 1 and we end at 3. We just want the area between this interval. Our width is 1/2, so the next line over is a 1/2 unit from where we started, which means that this is 1.5, and then the next line over is 1/2 from the previous number, which is 2, and then this is now 2.5. So that's kind of like your preliminary step, and then your next step is to construct 4 rectangles starting on the left side. So what you do is you start at the left endpoint and you draw a bar until it touches the graph. Draw a bar until it touches the graph. Okay, and then for now, go ahead and continue to move on to the next point. Draw a bar until it touches the graph, and then notice that I made the dot where it touches the graph. I made it really big so that it stands out, and then I draw this last bar. Okay, and you leave this bar alone. Do not draw the bar at the last endpoint, because we don't need it. Since it is a left Riemann sum, we start on the left and we leave out the right. Okay, and here's what we do next. The location where I put a big dot, I'm just gonna draw a bar over it. Okay, draw a bar over it, draw a bar over it, and then draw a bar over it like that. Okay, so I am approximating, and now I'm gonna kind of connect this down, but remember I didn't put a dot here, right? Okay, so now I have 4 rectangles. I started at the left Riemann sum, and for each rectangle, I'm able to find the area of each rectangle by taking the width times the height. And what I'm going to do is I'm going to add all of them up, and whatever I get is the approximated area that's below the curve. Okay, now keep in mind that the true area below the curve is all this region right here. That's the true area below the curve. However, when we use the left endpoint approximation method, we are able to approximate its area, but it is what we consider an underestimate because we left out these pieces. So would this approximation be an over or an under? Well, it is an under, because if you look carefully, all these strips are below the graph, so therefore it's under.